all of the different ways in which we have talked about doing things in R using Google Colab, and put together kind of a video that you guys can rewatch when you're going through this. So as we think about this, these different experiments, one of the issues that's really big in this lab, and we'll show you this towards the end, is that we're completely ignoring any heat that leaves the Yeti cup. And because of that, every single one of these has a huge systematic error, and therefore a fairly decent size percent error. Sometimes latent heat diffusion can have a small percent error, but it typically does have a large percent error, and as well a systematic error. So the computational physics or the theoretical physics via Colab simulation that we're going to look at today, you do not have to execute that today at all. We're going to do an introduction to that, but you can actually write your lab report with a spreadsheet, and the spreadsheet generated the data using this code, but it already is there and available, and you can download it or link to it, I think from Piazza, but I can also put it in the text box. Now, we got this information from people in lab, and for some groups yesterday, we got the information from the table that is actually in the lab. So the person who has their colleagues in the lab and they're actually online, this will help you help them when they have a big percent error to be able to describe this as we go through that. For those who don't have anyone in lab, you're free to just use this data from here, but we want to go ahead and get started with understanding Colab. So one of the reasons we are starting with Colab, and before we get really started with Colab, I want to say that, you know, we have been working on this with those in biology. I think the discussion with Professor Lewis happened about 2 years ago when we were just talking about the many difficulties associated with Excel and add-ons and the problematic aspects of Excel that different people face, or Google spreadsheets. And so in physics, we've been using graphical analysis, but I have been counting the days when 2 years ago, they started using R in the intro biology classes, and other people have started doing either R or Python in other labs so that we can move away from graphical analysis and do things in Google Colab. So I'll ask the question, you may not remember this. There was one student who said, oh, I do have R on my laptop. We must have done it in a class, but I don't remember it. How many people either are using R/Python now, or some other computer code now, or have the program in the computer or on your laptop, I should say? So you can just say, yes, I have it, or I've used it, or no. Go ahead in the chat box while you're online, fill out this chat box. Because we're trying to get everyone's feedback on this, and we're also trying to make sure that everyone's paying attention and not tempted to do anything else online. Make sure everyone's on the same page. All right, is this everyone? So it looks like we have 1, 2, 3, 4, 5, 6, maybe 7 no's, 1, 2, 3, 4, 5, 6, 7, 8, 9, maybe 9 yeses in one way or the other. So a little more than 50% yeses. So biology and neuroscience, they can do more advanced things in their actual classes if they're not using data that's just kind of fake data or, you know, old data. But if they can use whatever is actually recent published data or data sets, and there's a lot of those in the cloud. Somebody was telling us yesterday that in one of their classes, I think a neuroscience class, people are using data sets in Python. Is anyone in this lab in that course? Maybe not. Is there anyone else who is in a course right now or recently who have used big data sets in Python or in R? Biostats. Okay, what George, what data sets have you guys used?
That was like last semester though, so it's not this semester. But we did like a lot of, I think one of them was something to do with like they measured trees and I don't know, just like a ton of like bio related data sets, mostly nature stuff, but
Mostly nature things. Yeah, I saw one yesterday on the United States data associated with heart conditions. Another one, of course, there's tons on about Colab right now. Not Colab, COVID. Catherine, you've used it too?
Yes, I have, but I took biostats at a different university last summer. But yeah, I used similar biology big data sets.
Do you use any DNA?
No, I have not yet used DNA.
There was someone who was telling me they were working on liver, things associated with liver, and I think they were working on various markers for the liver and different aspects. And I don't remember all the details, but you can get, papers now that are published have to give access to the data so other people can reproduce the results. So a lot of this data now is available online in one way or the other. Some big data science things are available online. So we can start bringing this into labs so that as people take advanced courses, people are not having to teach the programming. They can immediately start implementing and start getting into the depth of what they want to cover without having to cover this. And thankfully, physics is one of the courses where everyone has to take it. And because everyone has to take it, it's a nice pipeline, especially for the advanced courses. And so Professor Lewis, especially Professor Olson and Robichaud were very excited about physics choosing to do this. For me, it's also this idea that Google spreadsheets can be quite annoying. And so, what did you guys think for the spreadsheets? And I'll just type this in as well. The spreadsheets for PLS I for the final project and or Lab 6. We had spreadsheets, you could share them, but now there were a lot of calculations being done. And so what did you guys think for PLS I, the spreadsheets that were shared with you? Easy to use, hard to use, difficult, not a big deal, complex? Great. Yeah. The other problem with Google spreadsheets is as soon as a TA touches the spreadsheet, if there's one mistake that's put on it, everyone then has to go fix it. And it can be quite cumbersome to go about doing that. It is a little bit tedious. So, however, before we get into that and what we're going to do to replace spreadsheets for your benefit, actually, both in terms of your career, the advanced science courses you're going to take, and in terms of just making the physics lab analysis much easier, is let's go back when we first told people we were going to do lab reports in Google Docs and use the AIP formal template. People were really worried about that. So how do you guys find the lab report template that we actually share with you guys? Was it fairly easy to use, the lab report template? And if everyone could please comment, that'd be good. All right, and it is also, turns out, with the template, it's an actual easy way to communicate comments by the lab TAs and record them, and then allow you to do a resubmit very quickly, usually without much time spent on the resubmit, because the comment is exactly where you need to make a change if in fact you had to do a resubmit. So the Google Docs, we've got to a good place with the Google Docs. In terms of the Google presentations, when we first started talking about, we're going to do presentations and everyone can choose a different final project. We'll have basic goal, linear and rotational motion, and everyone will give a presentation, even though it's a large group. And there'll be 3 slides, a design slide, a data slide, and an analysis, sometimes a 4th slide on error. What do people think in the final presentations on their Google presentations? We had a bunch of examples that you could look at. So everyone had their own example set of slides. Feedback on that? We did figure skating, yep. Other people? Yeah, some people just did, yeah. Feel free to just say good, fine, no problem. Simple is fine. Yeah, and the carrot. We had a lot of carrots yesterday. Just like what they said above. Okay, so today we're going to start Google Colab, and the hope is, one, it's going to resonate with your career. I know there was a science business major who was previously who joined my research lab and was worried about learning how to computer program because he hadn't learned it. And I was like, oh, I can teach you in an hour. Just give me an hour. And then you can pick it up and go with it. And he was really surprised because he had heard that it was much harder to do. For those even in science business, you may already have access to computer programming depending on what you're interested in, but it is great to develop your own models in business because you can grab all kinds of stock market data. You can grab World Bank data. There is a lot of data even for business, actually in everything. There's not a discipline in which there's not a bunch of online data out there that can improve your career if you know how to use it. I'm working with some urban planners who are using GIS and public policy, and all the kinds of maps are also available on Google Colab. You don't have to use ArcGIS or other types of programs. So we will always have an actual Google Colab file that you can start with and then edit. So I'm actually going to start with this one here, and I'm going to give you guys access to it. I just want to make sure one part of it. Yeah, okay, good. So if you guys can go ahead and click on this link, go ahead and see if your computer opens it. Sometimes you need to be logged into your University of Notre Dame account, but it should open up. If you do that, if someone can volunteer to show their screen, please share with us where your screen is. You need access. Okay, thank you, Ava. I maybe didn't share this one because this is a brand new one. Hold on one second. Oh, it says everyone should be shared, but that's okay. Hold on. Anyone with link? So you can view it. You won't be able to run it. So let's go ahead and try this again. So it has a different URL now. So go ahead and click. Oh, whoops, I didn't send this to everyone. I sent this to Ava. Hold on one second. Let me send this link to everyone now. So can everyone open it up? Just yes or no if you can open it up. All right, Casey, do you have a microphone? Can you come off mute real quick?
Yeah.
Can you go ahead and share your screen so everyone can see what you have?
Yeah. Let me. Where did you guys go? Oh, okay. Yeah. Can we see? Is this the right screen? Everyone can see that.
Mm-hmm. So
Okay,
I
sweet.
need you to go to click File, and then click. Go ahead and show me. Save a copy in Drive, and everyone go ahead and do that. So now you actually have your own Google Colab notebook folder that immediately got created once you save one Colab file on your Google Drive. So before you didn't have a Colab notebooks folder, but now you will because you just saved this on it. You can also edit this all you want. This is now your file. But before we talk about that, let's make sure we can run this and it runs. So click Runtime up at top, and then click Run All next. And if everyone else can do that, what do you see at the bottom once it runs? You'll want to scroll all the way down.
Oh, it looks like it's still running, maybe.
Yep, it's still running, but that's okay.
Okay. All right. These histograms is what you're looking for?
So what you see is that it ran everything all the way to the end, and that little 22 bracket, that's how many outputs the code gave us. So there were 22 outputs. And so does everyone else, can everyone else run this? Can you say yes or no in the code? And I'll start sharing my screen now. We'll go back to mine and walk through what all this does. Thank you. Is there anyone who cannot run it? Because if you can't run it, we need to know now. And a couple people did have trouble yesterday, which we walked them through. So is everyone running it? I've only heard from 3 people. Okay, if people could not direct message me, it's really hard to get 5 direct messages. Just make the message available to everyone. It's okay. Everyone, in the chat box, there's a little button that says everyone or a specific person. If you could click everyone and then give a message, that'd be great. Okay, so I don't think I see any problems. Everyone seems to have run it. And I hope we have the 14 people who are in here. All right, so let's just go through this line by line. The one thing that you want to know is everything that's in white is text. And text is not code. Text is going to be links that we have that you might want to look at. We can put images in here. But this is nothing that will run the code or interrupt the code. The parts that are the code are these gray parts. And this particular first part of the code, you can see if you double click on it, you can actually edit it. But it's set up in a way that it doesn't encourage you to edit it because you really don't want to edit this first part of the code. This first part of the code says, do not run in Python, force Google Colab to run in R. Google Colab by default runs in Python, but because most of your classes are going to be using R, we are actually going to be using R. Now, the grad students are more familiar with Python, the physics grad students. And so I've just told them, you know, the syntax is a little bit different. Instead of these 2 characters, you would just use an equal sign. But we're going to use it in R just so the coding language is the same. And then later on, you guys can quickly use this in other courses. So now that we have it set up in R with this part right here, we'll run our first computer code. So our first computer code that we run, let's say we just look at this very first line A. So this first number here, 2021, is going to be assigned to the variable A. So anytime in the code you're using A will represent the number 2021. So you'll see if I just type the letter A, I'm asking the computer to output the variable A. So when I run it by pushing this little arrow, it runs this code and it outputs A here. And A is in fact 2021. Great. Let's output B. So I rerun it. And now this particular code, 1:100, gives me a string of 100, where from one part of the string to the end of the string, it goes 1, 2, 3, 4. It increments up by 1. Well, now let's do some math. Let's do A plus B. So if I do A plus B now, I'm now going to have 1 added to 2021. That's going to give me 2022. I'm going to have 2, which is the second string in B. And so 2021 will be added to 2023, and so on and so forth. So that constant A will be added to each part of B as if it's a vector addition. All right. So now let's say that we want to change this to 3 and actually have a string of 300. So now if you run this, if everyone can run changing the numbers in 3, give me your last digit. What is your last digit? I'll go ahead and run my last digit. Everyone go ahead and type in the chat box, what is your last digit? And so please put in your last digit so we know you're not having trouble running the code. All right, I think we have everyone there. Okay, so I'm going to go put it back to the original that we started with. And this is computer code, and you just ran your first computer code, albeit very simple, but you ran your computer code to do this calculation for you. If nothing else in the entire world, everyone should throw away calculators. Well, not really. You can use them for simple calculations. Everyone does. But sometimes I see people do all of their calculations on a calculator, and we have lots of them. Don't do your calculations on a calculator. Do them on the computer because it'll be much faster and you won't lose them. You can go back and look at it again. All right. If you were to do this in in Excel or Google spreadsheets, you would have to have a column of 100 cells, and then you would have to reference another cell for 2021, and you would have to add that particular cell to each one, and you have to remember, do I put a $sign? Do I not put a $sign when I copy and paste it? And so you'd have to have 101 cells, and then if you want to add it, it would be 201 cells. However, here it's just 3 lines of code. This is beautiful. It's simple. And then if you want to do things in a spreadsheet, you can actually go and copy it in a spreadsheet. So if I have a spreadsheet here, I just highlighted it, and now I can actually copy and paste it and put the values in a spreadsheet. So you can still go back to a spreadsheet if that's what you want to do. There's no problem in going back to the spreadsheet. It's just that we're now trying to leave spreadsheets. But a lot of people go back to a spreadsheet because that's where they feel comfortable with. And that's fine. I mean, there are definitely things that I want to double check to make sure the code's running. And so I'll put something in a spreadsheet just to triple check if I think a code's being weird. It's not unreasonable to do a spreadsheet. It's just nice to do things in computer code. And at some point you get to a point where you really can do everything in a computer code, all your graphs and everything. Now, sometimes you have lots of variables and you want to be able to create a print statement within your code that sends you text. that explains to you what you're printing. And so you'll want to just run that and see, like you could say, print hello world, love R, Python, or whatever in Colab, it doesn't matter. And then at the end, you could then say, maybe you wanted to change this and say, this is A plus B. And so if you ran it, it would give you the text, this is A plus B, and then it would give you the string that represents A plus B, the output. And so when you're looking at your output, sometimes you want to have text to remind yourself, what is this output again? Especially if your code starts getting complicated. So that's just how you do text. And I'll leave it back to where it was. Now we want to just not do basic arithmetic. Now we want to start using functions. And when we want to use it scientifically, and especially in a lab setting, we want to be able to create random numbers. So the first function to look at for random numbers is this function called run if. Run if will generate a random number. And so if you run this code, run if 1, can everyone please copy and paste your very first output, and your first output is just one random number. Now everyone's number will be different because everyone's computer will generate a different random number. So can you go ahead and put in what random number you got? Is there anyone who had difficulty running the uniform distribution function run if? Okay, good. So now we can say, well, now I want 3 random numbers. So if you notice the second line, that's the run if 3 numbers. And then you can say, okay, I got this. I want 1,000 data points, but I know what my range is. So I want some of the data points between 5 and all the way up to 10. And so I want a uniform distribution that between 5 and 10, everything is equally probable. And so if you run this here, if you can put your last number in here, let's see what our last numbers are. Because everyone's number should be between 5 and 10, but everyone's will be different, their last number. So go ahead and put your last number in. Great, so no one's having difficulty copying and pasting their last number in for that string. Great. All right, so because of the central limit theorem, we know in fact that it's very rare to have things as a uniform distribution. There are dice where 1, 2, 3, 4, 5, and 6, as long as it's fair dice, would be uniform distribution likelihood of any one of those 6 digits run. So if you just tracked how many you did, they would all be equally probable in any one run. And we know that in a measured lab, it's much more, when we take these measurements, going to be normal distribution. Because in general, there's actually a true value. And that particular true value of what we're trying to measure, the sensor is sometimes a little bit to the left and a little bit to the right of that true value that we're trying to measure, based on the uncertainty of whatever tool we're using. So if we look at now this white text that says what the next code does, you can see now that we can also add a link. So this link is hyperphysics talking about a Gaussian distribution function that's actually used to create this random number. And if you go down here, does everyone know or understand this, this type of distribution? In other words, a Gaussian distribution should be centered at 0, plus or minus 1 standard deviation. So if you look at the one standard deviation, that 68% probability that your data, all your data would be in here. 68% of the, however you want to phrase this, there's lots of different ways of phrasing it, but most of your data for one standard deviation to the left or the right should be within here, or at least 68% of it. Now, will there be a probability that there's some data point that comes up that can be generated that's way out, that could be all the way to positive infinity or negative infinity? Yes, but the probability that you would see that is extremely low. So does everyone understand what a Gaussian distribution is? This makes sense? Is there anyone who doesn't understand it? Okay, great. Awesome. Good. So we don't have any problems with this. So if we run this R norm now, instead of run if, R norm, it will generate one random number. So let's see what people got. So I just typed in mine. If other people can type in theirs. Go ahead if everyone else can type in theirs. Great. Oh, someone got really small. Yep. Okay, so you can see that it's randomly distributed. If we were to take enough of these data points, we would actually find a mean of 0. And if we were to take the standard deviation of all the string of these, we would find the standard deviation to be plus or minus 0.34, one standard deviation. So you can actually use this function and create another set, say 3 random numbers. If we want a big data set, I'm talking somewhere around 1,000, we actually can generate 1,000 data points. And more importantly, we can actually generate a mean. So we can shift it away from 0 to say 10. And we can shift the standard deviation away from plus or minus 0.34 to the standard deviation that actually represents the engineering tool we're using. So in this case, I just set it up to be 2. So if you run it now, just grab your last data point and put that in there. So for me, my last data point was pretty close to the mean. So 68% of all of these should be around 8 and 12. And you will see, in fact, most people's results are between 8 and 10 because that is a standard deviation below and above this mean value. In fact, I don't even think we saw anything below. Did we see anything below 8 or above? Yeah, we saw 1. Sarah had above a 12. Well, most people weren't. Now, when you think about these codes, you could have an extreme outlier which gets outputted. So we'll talk about that later because an extreme output in a computer random generator is not actually physical. You wouldn't find something that would be 10,000. Like we're not all of a sudden going to measure, 10,000 degrees in the lab today. No one will see that. So we'll trim extreme outliers out. But other than that, this gives us a really good random number generator that the normal distribution will represent the engineers who have tested it to actually have that standard deviation in the measurement. And we can talk a little bit about estimating the process error from that by adding more to the standard deviation. All right, so we'll keep going. So we know we have these functions. Now we want to assign variables to these functions. So I can assign just variable 1, 2, 3, 4, 5, 6, 7, 8, and I can have all 1,000 data points, but I can change the mean. And so these have 10, but then their standard deviations are different. So maybe they're using different engineering tools. Some of the tools have a bigger standard deviation, they were cheap. Some of the tools have a smaller standard deviation, they were more expensive. We could also change the mean. Maybe on average, there is a different initial temperature or final temperature for this metal. And so we would shift it, the mean over. And then maybe they were all using the same tool, the same temperature tool, and it all had the same standard deviation. So there are lots of different ways that you can generate this set of random data. Now, again, just to show you how quick it is to get a big data set, here is a graphing example where we just installed Tidyverse, and specifically the library that comes with Tidyverse. And you may have used this particular library in your biostatistics. Many times in biostatistics, you do this vehicle analysis and do statistics on US vehicles or international vehicles. So we download this library with 2 lines. It's just 2 lines. It installs it very quickly and easily. Well, I said quickly and easily. Yep, there we go. And then we can actually say, hey, grab this MPG information from here. So it graphs it. I mean, it plots the table of what is located in MPG. So I only had 1 line of code, and then I got this whole data output, which is the vehicles, engine displacement, type of vehicle sold, the year it was sold, the engine size, something about the transmission, and the fuel economy for city driving and for highway driving. Okay, and then you do 2 more lines now, and now you can graph it. You can graph the engine size and the highway fuel economy. So the larger the engine, the lower the fuel economy. Well, the larger the engine, the more power you have. If you have more power, your fuel economy is going to be less, because fuel economy is related to the efficiency of the vehicle. So within 5 lines of code, 1, 2, 3, 4, 5 lines of code, I'm able to get all of this data here and plotted. So that's pretty easy, much, much easier than if people were to give you a Google spreadsheet of all the vehicle data and then have you actually create a graph in there from that. It's not totally convincing that this is much easier. So we'll do a little bit extra to show how much easier it is. So we'll look at some of this random data that we created. So we created a set of random data here. And let's just look to see if that random data that we created was in fact a Gaussian distribution, because we claimed it was a Gaussian distribution. And I'll have one person share theirs. Nicole, could you share, after graphing simulated data, what yours looked like?
Yes. Do I just run it really fast and then that'll show like the new one?
Mm-hmm.
Okay.
We're not going to be able to see it unless you hit clear, share screen though.
Oh yeah, sorry. I don't know what's going on with I updated my computer and it's saying I need to figure out how to share the permissions with Zoom.
Oh, okay. Hold on. Let me see. Make sure that you should be able to share. Or maybe you're having trouble.
Oh yeah.
Can you do it? If not, we can switch to someone else. It's okay.
Okay, sorry. It might take me a second.
No, it's fine. It's fine. Catherine, what about you? Were you able to do it?
Yes, I was able to do it. Would you like me to share my screen?
Ava, try it again. Click run all and see if it'll do it.
Okay, can you see my?
Yeah. So do you see that yours is at 10? So your mean is at 10, which is what we set it to be?
Yes.
Now, if you were, I can actually look at yours and look at mine. You can only see yours right now. But as I look at yours, your value for your mean, there's about, what, 100 and maybe 80 or 90 incidences where they're around 10. And to the left of yours, it's actually bigger. There's more incidences slightly to the left at 9. and it's at 11, you're a bit lower. And mine is equal at 9, and my 8 is actually much lower. So let me share everyone my screen. So can people see my screen now?
Yes, ma'am.
Okay. So in this one now, you'll see mine are actually equal and this one's lower, not higher. So your Gaussian distribution will in fact have a mean of 10 and have a standard deviation of 2, but everyone's data will be slightly different because we used a random number generator. So just to be aware that you shouldn't expect exactly what I have on my screen because you have your own random data. Does that make sense? Everyone? Yes, no? Yes.
Yes.
Okay. So now if we go to, okay, so where in the world are you going with this? This is not physics right now. Well, now we're going to make it physics. Okay. So let's say we have a bunch of simulated data, but that simulated data is supposed to be masses. And then we take the masses and we're going to multiply the masses times 9.81 meters per second squared to get the weight. And we're going to just call the masses x-axis and the weights y-axis. So we can actually plot this now. And when we go to plot it, the very first one is the simple plot. And you'll notice that one has no title and it just writes down on the axis whatever you put inside here. So the second one is actually much better of a plot because now we can change the name of the axes and the title. And later on, we'll have some features to be able to actually easily add error bars and minimum and maximum. So we just push that button and it immediately generates. We don't have to click through all the Excel options. We don't have to like highlight columns and like, oops, I accidentally hit 2 columns and now it's doing a series instead of just the data that I want. There's no fighting about it. You don't have to futz with it. You just push this little button here and it generates a graph for you. So this is going to be a set of data. And then this is what we're going to calculate. Now let's see, we can use not only a linear function, let's say we want a sinusoidal function. So we can actually use the sine function. R will have all of your normal mathematical functions, tangent, cosine, exponential, logs. And there's a cheat sheet for all of that. You can just do R language cheat sheet and you can see what all of the coding is for that. So now we have data. And remember our data was Gaussian. It was, you know, the mass was 10 and it was plus or minus 1 standard deviation was 8 to 12. But every now and then we might have measured it to this particular data to be a little bit more or less. We might see some others. So when we put it into the sine function, it makes sense that it's not evenly distributed in this sense. If we had done a string of values for x where they were equally distributed like we did for the variable b, then you would have equal data throughout. But in this case, we don't. Well, that's exactly what we want for what we're doing in this lab. We actually want these random data that represents our mean that we measured in the lab and then a standard deviation around that. And lab people are like, well, but you didn't have the exact number. And we keep saying it doesn't matter because that exact number is only dependent on your standard deviation accuracy of your engineering tools. So sometimes people have, you know, 3 or 4 or 5 sig figs when you don't even have that little level of accuracy. And so you'll start to see that here. So we have for this specific heat, and we have the same one for latent heat diffusion, or I mean, it's different in the coding, but it's a Colab file for that, and we can share it with you. In this one, we have the initial temperature, and this was actually from, I think, table C in section 5 yesterday. And they had a whole bunch of data, but all we asked for was, when you went to go start it, what was the initial temperature of the metal? And then we wrote the standard deviation, which was a little bit more than the sensor. The sensor was 0.5 degrees Celsius, and we put 2. Because we said there should be some little bit of process error. And then we put the final temperature, 17. They were like, well, but some of our runs, it ended at 19, and some of our runs, it ended at 15. But yeah, we don't care. We're just going to do plus or minus 2 standard deviations. And then the water started off cold, 5.6. It ended warmer after getting some of the heat flow from the metal into the water. And for this particular run, it was 17 plus or minus 2. And then we had the mass of the metal, which was, you know, our scale is pretty accurate, 1 gram. So in kilograms, it's 0.001. And so we had the mass of the metal that they put in, the mass of the Yeti cup, and the mass of the water. Then we have a set of specific heats. So you can actually change this code if you were looking at something else. In this case, we used, this was an example for copper. We have another one for aluminum and another one for steel. And so we run this, and you actually don't see the code right now. But if I get rid of this little hashtag, which said ignore anything afterwards, because that's just text, and I rerun it, can everyone delete the hashtag and then write out the very first data point? So all I did, I had a hashtag here, specific heat, and I just deleted that specific heat and reran this code. And then I put the first number, which was originally with that random code. And now I ran it again, and now I'm getting a new number. Okay, great. So you can see that there's actually 1,000 different data points that we used, albeit generated data points. And so there are going to be 1,000 different calculations for specific heat. So I'm actually going to recomment that out so I don't see all of that data. But what I want to do is get a histogram of that for every single calculation of the specific heat. And I want to get an average and a percent error. So if I run it, if everyone can go ahead and put in their average for the specific heat, go ahead and put in your average. And then after you put in your average, go ahead and put in, once people have that, we'll give them a few more minutes. All right, so now we'll put in your percent error. Go ahead and put in your percent error. My percent error is like 95%. And I'll wait yep, there we go. Okay, so this is an example where people are like, oh, I hate physics labs. Percent error is so high, right? Everyone, anyone want to own that? Yep, thank you, exactly. But it's because we assumed something in our equation. When we did this, our calorimetry is just a Yeti cup. And in fact, no one puts the top on the Yeti cup. So is it really a closed system? People on chat, is this a closed system? If we just have an open Yeti cup? No, it's not a closed system. So we have heat loss that we just ignored as physicists. Well, because for us, it's just systematic error. So what if I add a heat loss, which was originally 0, and now I'm going to add a heat loss and rerun the code. And when I rerun the code with a heat loss of 6 joules, I'm now going to have a percent error of 31, which means 6 joules now I've modeled have left the Yeti cup. Well, it turns out it's a little bit more than 6. So play around with this value of a heat loss and keep playing with it till you're around 0% error. What do people get at? What is their heat loss such that they see pretty close to 0% error? This might take a couple minutes, and feel free to ask. Remember, you're going to have to press play on the first one and then play on the second one. So you're gonna have to run it twice, or run the top one and then run the bottom one. So Margaret, what are you getting? Can you come off mute?
Yeah, I tried 10 and I think I got a 6% error and that was the lowest I've, or no, wait.
Okay, try 11. What do you get with 11?
Okay, one sec. With 11, I get a 0.57% error.
Yay, and people are saying, oh, try 11.5. So let's all try 11.5. So somewhere between 11 and 11.5 within the random number generator, we're getting pretty close to 0%. So Margaret, how would you put that into words if you were to talk to the people in the table? Do you know how you might say that? Like in terms of systematic error, maybe I shouldn't call you, put you on the spot. Let's open it up. Anyone, how would you describe what we just did to explain why our percent error was so big? Because initially, the model that you use in lab today, that everyone's using in lab, they're going to have a high percent error. And we're okay with it. But what can you guys do using this code to help them understand how to explain their percent error being so high? Anyone want to take a stab at it?
Well, I can try. If you don't account for any heat loss, like if you say that the heat loss is going to be 0 joules, then your value is going to be far off from the actual like literature value, which that makes the percent error really high. So when you account for that like heat loss and error, then it makes it go down a lot.
Exactly, bingo. So when we graph it, our theoretical value is 385 for copper. So let's just think about this graphically because we did those worksheets, right, on comparison based. So 385 is right here. Can you guys see my cursor? Yes?
Yep. Yes, ma'am.
So is this 1 standard deviation away from where the mean is that we have? Because our mean for all of these values is right here. Does that look like it's 1 standard deviation away?
No.
No.
Oh, really? Or maybe I'm saying this wrong. So if our mean is here, plus or minus 1 standard deviation is right here, correct? Or let me ask. Maybe I can ask. So if you were to look at this graph, which is every single specific heat value we have, because remember, we have 1,000 data points. So in my graph, 194 of the data points is around here. 182 of that 1,000 is here, and 186 are here. So between here and here, I have 68% of all my data, correct? All my generated data. Does that make sense? I need to actually talk to someone. Does anyone, let's see, who can? George, can you come off?
Sure.
Okay, great. So 1 standard deviation, if you were to just look at this distribution, can you talk to me about where you think 1 standard deviation might be? Just
So like,
approximate.
if there's 1,000 data points, I think 1 standard deviation was 68% of the distribution. So that would be, it would like, you would have to, I guess, count the frequency, and you would have to like count from the middle 340 from each side, because 340 on the right of the mean and 340 on the left of the mean would be 680, which is 68%. So that's for your 1 standard
So
deviation.
it's 117, 134, 182, 186, and 194. Is that 600?
So you have what was it? 182, 194. Yeah, that's roughly 600.
Exactly. So right in here is 1 standard deviation to the left and right of the mean, correct?
Yeah, that sounds good.
Okay, but we actually calculated our value to be 766. So our actual mean is right here, correct?
Right.
But our theoretical value for copper is 385. Our theoretical value is way over here. Is this outside one standard deviation for sure?
Yeah.
So there's definitely systematic error, correct?
Yes.
So we would expect, given randomly generated data, that even if they were picture perfect in their lab, everything was beautiful. They did their procedures correctly. They used their tools correctly. They had a little bit of a process error, and they were perfect human beings in this lab, perfect scientists. We expect a systematic error because of the model we used, correct?
Yes.
So this is not human error. There's no human error in here. The only thing is because we can't account for the heat loss. Does that make sense now? How to go about and see these, how do you say this? So many times in lab, people want to say, well, you know, we did this, we did this, we did this, and therefore, you know, it must have been a problem with the way in which our, you know, the way in which we carried the Yeti cup from the hot water to our actual measure sensor. It's like, no, actually, you could do that all day long. I don't care. You can do that from nighttime to morning. You can do that in the summer and winter. You're fundamentally going to have a problem. And the reason is because we can't actually measure this heat loss. It was the same thing with the ball drop. You can assume that there's no friction and the ball drops really fast because there's very little air friction. But it turns out the air friction is still significant. And it just depends on how long they kept the Yeti cup before they reached equilibrium as to whether or not this was a big effect or a small effect. And likewise with the friction one, whether it's a bigger effect or a small effect, all depended on the surface area of the object they dropped, and whether or not it reached terminal velocity when they did drop it. So likewise in here, we expect in this lab to see systematic error, and it's not a problem for physicists. And this, I think, helps to be able to make explicit and visible the types of things we're talking about when we talk about the difference between random error and systematic error. So now you can use this code if you want. You can actually play around with this number and talk about that, especially for the person who has 2 people in the lab today and it's isolated. They're going to think you're brilliant to be able to describe that. Who is it that's isolated?
That's me.
Oh, it's you. So if you can just grab their temperature data in mass and say, oh, I don't care, just approximate it. You're going to drive them crazy. They're going to give you 4 digits. It doesn't matter. Just take their data and generate it, and then just change that heat loss, and you're going to be able to give that to them. That makes sense?
Sounds good.
Yeah, they're going to think this is awesome. Well, based on the other people in the lab, they are. So what does that mean? Well, if you want to read all of the details about how you interpret setting up the mean and the standard deviation, the mean is also approximately what data they took. And then the standard deviation is the actual sensor uncertainty. And usually you add a little bit more for process error, not for mass. There's really no addition or subtraction of the masses they use. Mass isn't just falling off these objects or adding to these objects. So there's not much standard deviation to mass, but temperature, there's a lot. And if you are writing the lab report and you aren't working with anyone in the lab and you're like, what do I put in that data section? Who was the one who showed their design slide? And I said it was brilliant, minus the need for an apparatus drawing. Do you remember which group was that?
That was Sierra, my group.
Okay, Sierra. So now you can actually look and you can grab this data, or you can actually, if I copy and paste this histogram code here, and I put this in here instead of the specific heat for the variable, and I'll just put a hashtag here, comment it out. Now you can actually say, this is the data that we generated for our lab. And Sierra, that's what you said you were going to do, right? I'm sorry, I couldn't hear you.
Yeah, that's what we want to do.
Yeah, so it's right there. And you can put that into your generated data section. Does that make sense?
Yep, thank you.
Yeah. So some people might be completely overwhelmed and they say, no, I'm not ready for code. That's totally fine. If you're not ready for the code, just use a spreadsheet. We have a set of data here. Go ahead and calculate the specific heat of steel and do the error propagation. Everyone has to do the error propagation this week. Because PLS I did not go through it so well, as we have seen, we want you to turn in a rough draft of Lab 1 next week, next Thursday. But, and we'll give you comments on it, but not the analysis section for error propagation. We are going to spend a little bit more time on error propagation and regression next week to make sure that everyone's on the same page. As we tried to go through it, both Fry and Martin and myself in the lab this week, it was, I think there were people trying not to cry because it was too stressful. And we just said, you know what? No, we're going to back up, put the brakes on. And we're going to make sure we cover over this and go through the worksheets and make sure everyone's on the same page. So we're going to back up and make sure everyone's on the same page. But this is your introduction to Colab. And these files that you'll want to look over. Just out of curiosity, what are your thoughts? Because I will put this on so you can rewatch it if you want. I'm going to put it on YouTube as a playlist so you can just go to different parts that you might want to listen to. But what are your thoughts for your first introduction to Colab? Is it hard to computer program? Easy, stressful, complex, have no idea? Oh my goodness, this is so easy, simple. What are your thoughts? Be honest, it's fine. Some people put Monday, you know, they were a little bit stressed.
Could I tell you my thoughts and ask a quick question real quick?
Absolutely. I'm fishing for people to talk. It's just
No, of course. I understand. My thoughts is it looks pretty simple. Like even now I kind of messed up because I'd be pressing enter to enter things and I actually like put to enter and I have to go back and make sure I just do that. So I have to get used to that. Other than that, my question is, you for Sierra, you just told like we had to do our data. We just like copy and paste and we can just do the data that we got randomly generated. Do we just use like one other group's data, like one group member's data for our lab report, or would we use like all of ours? That's kind of my question.
Literally, you can use this spreadsheet and you don't have to do anything with Colab.
Okay, I see what you mean.
Like just start to look at Colab and start to get an idea, but you do not have to use it. If you run into problems like you just said, oh, I changed one thing, now I'm getting error codes. Well, then don't do it. Go to the spreadsheet. No stress.
Okay, perfect. Thank you.
Yep, not a problem. Some people are going to find it really easy. Some people are going to say, you know what, I'm not ready for it yet. But we'll go through it again. We will look at it with regression and show how much easier it is than the graphical analysis in regression, show how easy it is to put error bars on it. People will then have run it again and seen it again another week. And then we'll see how we go from there. Different people write different sections of the lab report, as everyone knows. So not everyone has to be doing this. Probably there will be someone in most groups who get pretty good at doing this, but we'll do a whole nother lecture on Colab. Other questions, thoughts?
Yes, I have something to ask.
Please.
Okay, I thought like today wasn't too bad, but we're not gonna ever have to like come up with our own code, correct?
No, I don't believe in that. That's why I started. Do you like your templates? Yes. Do you like editing your templates? Yes. Do you have samples? Yes. And most of the other groups, I showed them an actual blank one. And I said, you know what, if you had to write a lab report and everything was blank, wouldn't that just feel awful and intimidating? And the answer is yes. But when you join a research lab, or even when you start a project, you never start with a blank slate. The real world is we stand on the shoulders of giants who've gone before us. And then we take the baton from where they left it off and we run as fast as we can with our own baton. And so that's what we're asking you to do. Just run with it. understand where you're at, where you're going, and then take it and go. But you will never have a blank one.
Okay, thank you.
Yeah, no problem. I mean, I have a feeling that other classes are going to give you blank ones, just heads up. So it's one of the reasons why you might want to start doing this, just so that when you have to do it in class, you actually already have experience with it. It'll be much easier.
Okay, thank you.
Yep, no problem. So we are going to go into breakout rooms now. I am going to have to assign people in some breakout groups because people have still been changing. So just, it goes pretty quick. Make sure you know what table you're in because it goes quicker for me. In probably 20 minutes, Fry's going to want to do a little bit with error propagation. So we'll talk a little bit about error propagation, but we're going to do much more next week. All right, I'm going to open up breakout rooms.